So this is the presentation of the paper, A New Heat Source Model for Keyhole Mode Laser Welding. And my name is Kristina Wärmefjord. I work at Chalmers University of Technology in Sweden. And this is Samuel.
Yeah, my name is Samuel Lorin, and I'm a researcher at Fraunhofer Challenge Center, also here in Gothenburg.
And other co-authors of the paper are Julia Madrid and Rickard Söderberg. So this is the outline of the presentation. We'll start with a brief problem introduction. We'll talk a little about variation simulation. And those are mainly the whys, why we are doing this. And then we get into the detail with heat source modeling. So that is the how we do it. And then we'll finish with future work and a summary. And as you see from the title, this paper is about a heat source model. And it is quite a detailed, technically detailed paper. We will look at this laser beam angle. I will just point here, you see that we have a laser beam for welding. And if we tilt this laser beam a little, what will happen with the welding? Will it change the look of the weld, the shape of the weld? Will it affect the distortion of the parts that we are welding? And so on. So this is what we will investigate in this paper. So to start with, I will say a few words about geometrical variation, because that is the background to this. So in the research group, we work with geometrical variation. So we have geometrical variation on individual parts. So they vary in form and in size. We have assembly variation. So we add some variation during the assembly as well, in fixtures done by manual assembly and so on. And this might lead us to products that do not fulfill our requirements. It can be assembly requirements, so we cannot put the parts together, they do not fit. Maybe they fit, but they do not function as intended. Or it can be perceived quality requirements that are not fulfilled. And that is the way the parts look together, the product look together. So you can see here some split lines. So that is especially important perhaps in automotive industry. You really want nice split lines and so on. So this is the background, the problem. And in the research group, we have a toolbox addressing those problems. So if we think of the product realization loop, we have some early phases during the design stage. During this stage, we can do robust locator design. So we try to find robust concepts that suppress variation. We can do variation simulation, which I will come back to in a minute. We can optimize joining sequences and the welding process. During pre-production, we work with inspection data, how to place the inspection points, what to measure, and so on. During full production, we can use simulation models to do a digital twin of the product, where we can individually adjust the processes. So given some parts, we have scan data of the parts. Given the shape of the parts, we can adjust the joining sequence, for example, or some other parameters to optimize the geometrical quality of the final product. So those are tools to address this geometrical variation and minimize its effects. I said I will come back to the variation simulation. And here we see the variation simulation. The purpose of variation simulation is to predict variation on assembly level. If we have those parts, we get it from the supplier, for example, we know a little bit about the parts. If we have those parts, what can we expect on assembly level? So the idea is to start with here that we define part tolerances. It can be tolerances and assumed variation, or it can be inspection data if that is available. Then we build a simulation model in step 2 to predict this assembly variation. In step 3, we use this assembly model. We run Monte Carlo simulation. So we sample from the tolerances that we have on the parts, and we evaluate the result on the assembly. So we get a distribution of the variation on assembly by doing this. If we then fulfill our requirements, everything is fine. If we do not fulfill the requirements, we need to change something and iterate here. So then we maybe need to go back. Maybe we can change something about the locating scheme. Maybe we can change joining sequences. Maybe we need to change the tolerances on part level as well. So there are some different alternatives, but this is an iterative process normally to find the right tolerances and the right design concept. And when it comes to this simulation model that we build, it can be assumed to be rigid, so the parts are not allowed to bend, or it can be non-rigid. And for a non-rigid simulation, we need to represent the part by meshes, finite element meshes. We need to define all the locating schemes and clamps and so on. We need information about the joining process, and it can be welding, as we will come back to here. We need to know what material we have. We need to do something called contact modeling, which is the way to avoid that the parts virtually penetrate each other during assembly. And instead, we need to translate those forces to the parts to get a good and accurate simulation model. So this is about variation simulation. And if we go back to the product development process, quite often in this process, during those early stages that I showed before, we want to evaluate quite many different design alternatives. So you haven't just one design alternatives, you have a lot of them. So you can see in this picture here, maybe you have a lot of different CAD models representing different concepts. So in this case, we work with aerospace industry. So here we have a turbine exhaust case. It looks like kind of a wheel, as you can see here. It is this part of the turbine exhaust case. Those wheels, they consist of a lot of parts. They are welded together to form this kind of sectors, and those sectors are welded together to form a product. And to evaluate all those different concepts of this turbine exhaust case, we need to evaluate all those models. And there can be different kind of evaluations. So maybe we need to do some kind of aerodynamic simulation, but we also need to evaluate how the welding affect those parts, because we do a lot of welding. We weld together those parts here, and we get the sub-assembly. We weld all those sub-assembly together. And as you know, when we weld things, they distort because we add a lot of heat, and this heat leads to distortion of the part. And usually, or normally, we do not want this distortion, of course. So we want the part to be as close as nominal as possible. So we need to minimize the distortion, or at least be able to predict what distortion we can expect and see if we can live with that distortion. But then we have a lot of different design alternatives to evaluate, and we need to run this welding simulation. And welding simulations are quite time consuming because we need to do temperature calculations, we do mechanical calculations, we do this on finite element meshes and apply finite element analysis. So that takes quite a lot of time. It's not unusual that the welding simulation can take many hours to conduct. And if we also want to include this in variation simulation, where we run Monte Carlo simulation and we sample thousands of samples, then this is not possible to do for this kind of variation or welding simulation. So we have a faster method, and this is based by some early work by Samuel. And here we can, I didn't change slide, I thought I did. Here it is. So then we have this fast method instead. It's called the SCV method. And that stands for, first of all, we do a steady state thermal analysis. We calculate the convex hull of this two-dimensional melting region, and then we apply volumetric shrinkage. So one can say that with this method, we calculate the shape of the melting region, and we do that in the middle of the weld, so we get this steady state behavior, and then we apply it, and then we allow the parts to shrink, and we see what distortion we get. And this method is much faster, so it maybe takes like minutes instead of hours. And perhaps a little less accurate, but still enough accurate in most cases in order to be to evaluate different design alternatives to do this kind of screening. So we use this method. And if I go back to this one, you see here that we have all those design alternatives here. And using this faster method, we can evaluate them and see what distortion we will get from the welding. But that is not the only case, the only thing that we need to evaluate, because sometimes there is a problem with the accessibility. So as you see here, those are kind of complex geometries, and it's not obvious that we can access the welds with the welding gun. Maybe they are blocked in some way and we cannot weld too close to another part, perhaps, because then we do not get access. So that is also something that we need to include in this, this screening of different design alternatives. But one thing that we have when we look at accessibility is that maybe sometimes we need to tilt the welding gun a little. So you see here in this illustration here, if we weld with a small angle for the laser beam, maybe we can access them. Then it's easier to get this accessibility. But if we do that, what happens with the heat that we apply? So how does this affect the distortion and so on? So this is the background why we need to have this heat source modeling where we have a tilted welding beam or laser beam, because for some design alternatives, we need to tilt the laser beam in order to get access with a welding gun. And then, of course, we need to include this in the simulation when we evaluate distortion. So that was the background. So I will leave to Samuel to explain the details of this welding and this heat source modeling.
Thank you, Christina. So, looking at a video here, you can see a weld robot that moves around in a weld path. And if you look carefully, you see that the weld gun is not perpendicular to the surface that is welded, but that is the case in the simulation movie you see to the right. So as Christina said, we got the question, what if we need to tilt the weld gun? What would happen to the heat source or the melt zone? And we didn't know that, and we couldn't find the answer to that in the literature. So we decided to do some experimental welding where we tilted the beam angle. And here are some examples of what we saw there. And you can see moving from the left to right, you increase the tilted angle from 0 degrees to 90 degrees. And 90 degrees was the maximum allowed tilt angle. So that is why we got those angles. And also you can see that you have this characteristic keyhole melt zone that I think we could have a look here at the schematic picture of that. So at the top here, we see something that we call a convective area, where we see kind of a more convected melted zone. And below here, we have something that we call a keyhole that comes from a digging of the melt of the heat source. The laser digs down deep, and this, of course, this appearance, it comes from the melt pool dynamics and vaporization and stuff like that. So it's pretty complex phenomena here. And if we look at how we simulate or model the heat transfer, I just included this equation here. I will not talk that much about it, but this is the weak form of the heat transfer equation. And to the right, we have the heat flux that is an area integral. and you have the volumetric heat source as a volume integral. And the heat flux, it consists of 3 parts. So it's a convective part, that is the heat that is convected from the surface. And you also have a radiant part, that is the heat that is radiated from the surface. And you have some applied heat source. So what we can do here is to model what is the applied heat on a surface, or what is applied heat on inside the volume. These are the things that we are trying to model here. And looking at the history of heat source modeling, if we go way back, they started with some point sources and line sources where they applied the heat, and they obviously got some problem. You may end up, if you have a point that is the heat source, you may end up with infinite temperatures and stuff like that. So you realize that you needed something else. And in 1969, Pavlik et al., they proposed this surface heat source. So they distributed the heat input on the surface. So you can see it's like a circle here. And inside this circle, it's a Gaussian distribution. So for each point here inside this circle, you look at what is the value of this Gaussian distribution to apply heat inside the surface. And also, if you see the circle line here, it denotes inside this circle line, you have 95% of the heat that is inputted from this Gaussian distribution. And here you can see what it may look like if you apply a heat source like that. So here we can see the typical convective appearance here. It's rather smooth and it's almost like a half circle. But experiments showed that this was not accurate enough. So next, some author proposed instead to have volumetric heat sources. So 2 of the most common, one of those is the cone heat source that you can see here. It's a little bit similar to the circular surface heat, but you can see that the heat source also digs down into the geometry like that. And here also, I can mention you have a moving coordinate system, and the weld path moves in this path like that. Another famous example of this volumetric heat source is the Goldach's double ellipsoid. And here you have an ellipsoid in front that has a little bit of a steeper slope than in the back. And this tries to mimic how the dynamic of the melt pool will look like when the weld gun moves in front like that. There are some extension to this and some alternatives and combination also. And also there have been proposals where you model the melt pool dynamic and also try to model how the laser reacts to the melt pool and stuff like that. But typically these are very time consuming and usually not lead to kind of this engineering results of how does the melt pool look like in engineering application and what geometry will you end up with. So moving forward here, some of the answers that we were looking for was, if you look to the left here, can we expect an incomplete penetration when you tilt the beam for certain parameters? Here we see an example of a complete penetration that you typically want. And also, as I said before, we need to be able to predict the geometric outcome of the kind of the global geometry. So we believe that we need this kind of engineering heat sources when we can actually predict the geometric outcome. And furthermore, as Goldak states, one of the most stringent tests of the heat source is its ability to reproduce the melted zone. So that is something that we try to do here. And when we started to model, we looked at the kind of the standard welding heat sources that we could find and extension to these, but we weren't able to kind of reproduce this kind of result that I showed you before. So after trying many alternatives, we decided to propose a new heat source. And we can look at the figure here. It's a combination of a circular surface heat with a Gaussian distribution on top here. And then we have a cone heat source that we actually turned upside down. And if we write this, it can look like this. So on the surface, we have this behavior here, and inside the geometry, we have this behavior here. I don't think we need to talk about the details of the equation right here, but what is kind of interesting is that we could rather easily couple the top of the heat source with the convective area we can see over here. And we can couple this digging down of the keyhole appearance with the bottom here. So it was rather easy to look, for example, of what area do we expect to be the convective area in comparison to the digging area down here. And then we know something about how to distribute these two heat sources, because we typically know the sum of these two, how much energy we put into the geometry. So some results here. So using this new heat source, we were actually able to capture rather good how the appearance of the melted zone looks like. And this is something that can be quite difficult to achieve, actually, because it is kind of a combination of what is the speed and how fast do the heat that you put in diffuse. So this is not at all a simple task to kind of tune a heat source like this. And here we also see that we have this tilted weld gun, the result from that, but we also looked at varying thickness down here, where we didn't tilt the weld gun. So here in the paper, we go in a little bit more in detail of how we actually propose some heuristic models to find the heat source parameter to reproduce these kinds of figures. So in some conclusion, we have presented a new heat source here. It allows for simulation of distortion from welding when accessibility constraints force a tilted weld beam. It is intended to use for model to find the melt zone shape and for predicting geometric outcome. And we show that the parameters that we can find parameters to accurately replicate the experimental outcome, both from tilted weld gun and also from varying thickness. Some future work that we think that we could pursue is some automatic fitting of the parameter. You could perhaps use some machine learning or methods like that. And also widening the use of the heat source model. For example, what would happen if you tilt it for some reason into not in other angles than we proposed here. So that was a summary of the paper. And if you have any question, we'll be happy to try to answer them.
So thank you very much. I would encourage anyone who's watching this video to reach out to authors and email them their questions. So we will conclude this webinar right at this spot. Once again, thank you very much. Really appreciate your willingness to participate.
Thank you very much.
Thank you.